I just thought of a cool way to recharge a pneumatic cylinder, which would be rather than use. No, no, no. Okay, so in pneumatics, you've got your reservoir of air, then you use valves to redirect that air, like a compressor. So, an air compressor is key for pneumatics. And I just thought it would be cool if your pneumatic cylinder could be its own air compressor just by recharging the cylinder using, well, no, or you do still have an air compressor, but you recharge the air compressor using combustion. So like you pour in a little bit of fuel and you ignite it, and then the fuel expands in an explosion, which then increases the internal air pressure of your compressor, so that there doesn't have to be a heavy pump that recharges it. Instead, it's recharged through expansion of gases when you explode fuel. That would be pretty cool. That's like a fast recharging method as opposed to a pump that has to kick on. Then you could use 2 valves for that compressor to send air directly to a pneumatic cylinder, which it could then move back and forth at will using that compressed air it just generated through an explosion. So the compressor would just be an explosion capturing device, and it would just control one pneumatic cylinder through 2 valves and 2 hoses. The compressor could be the size of the pneumatic cylinder. That would save on weight, and you wouldn't have to have a big motor that has a pump for pumping up the air. And you wouldn't have to have any heavy valve control systems. It would just be a single... Well, wait a minute. Actually, you could have any number of hoses coming out of that cylinder. Huh. And each hose that comes out of it could be leading to one end of a pneumatic cylinder. So you could have a bunch of valves just coming directly out of that cylinder. Then being distributed anywhere you want. Oh my gosh. You could then have pneumatically actuated muscles which just blow up. Instead of like a cylinder with a piston in it, you could actually use muscles that inflate. Like the muscle bag design, where the muscles elongate when they're empty of air and then they pull in when they fill it with air. And a valve could control the rate at which the muscles fill with air, and therefore the rate at which the muscles are moving. You could have one intake valve on the muscle and then one exhaust valve on the muscle. The exhaust valve could be used to control the rate at which the muscle releases. It wouldn't be a pneumatic cylinder-based robot, it'd be a pneumatic muscle bag inflation-based robot. We could use pneumatic muscle-based systems in conjunction with DC motor-based systems. Perhaps using the pneumatic muscle-based for situations where cost would be more effective that way, and situations where we need more power than really DC motors can offer. I feel like DC motors would... I don't even know if they're better now. A single cylinder. Holy shit. Sorry for cussing. A single air compressor in the chest could have hundreds and hundreds of valves. Hundreds and hundreds of valves. And hundreds of hoses coming off of it of all different diameters. And that big cylinder could power huge amounts of the robot. Now, if any one of those hoses blew, the whole system would fail. But, I mean, it'd probably just have a leak. It'd probably just mean the cylinder would need to recharge more frequently. I don't think one hose flying off would ruin the entire robot. It would, so... If one hose blew off the big cylinder in the chest that's powering the whole robot, the big air compressor, that air compressor would have a leak and it'd just be spraying out air inside the robot like crazy. But I think it'd just be recharging constantly then. That would be the only difference. So it wouldn't really damage anything, and it'd probably let out a loud hissing, so you'd be notified right away and you could repair it. And that may not happen that frequently. I don't think it'd necessarily happen all the time. A huge advantage to a pneumatic-based robot would be the whole robot would just be a series of tubes leading into little sacks, little bags that could be located anywhere. And they would be a lot closer to the human body in that you could locate even a little bag inside a finger, inside the meat of a finger next to the bone. And that little bag could fill up with a little bit of air and just move that little finger joint. Just two little tubes leading to a little bag. One's a vent tube, one's a air intake tube. And you could have bags of all different sizes that act as muscles, and they can be located all over the place, all controlled through valves. And those valves can be as simple as... Oh, but you know what? Okay, so the valve would still require... Every single valve would still require a DC motor on-off. That one motor can probably control two things. It could open one valve while closing another valve. So it would probably control the valves of opposing muscles in order to make sure that one muscle is contracting while the other is filling. And at the same time that valve closes one muscle and opens another, it can be shutting off. Okay, so it could be shutting off. Well, okay, so you need three states. You need the muscles filling, the muscles just closed and holding its state, and then the muscles exhaling. So as the motor turns, it could pull a string. The valves can be spring activated, so the string just releases tension on the valve and the spring opens the valve. If the motor turns clockwise, it pulls the valve back shut. If it turns counterclockwise, it releases tension on the string and the spring opens up the valve. So it could be spring activated air valves that work the exact same way as a fuel injection valve on a car. Anytime that motor turns clockwise to shut off a valve, okay, that's fine. When it turns counterclockwise to release the string's pressure on the valve and open up the valve, at the same time that it's opening up the valve to introduce air into a muscle, the opposing muscle needs to have the same amount of air released from it. So when the motor turns counterclockwise to open up the intake valve of a muscle, the counterclockwise motion can also open up the relief valve of the opposing muscle in order to let air out of that muscle. Nah, I'd say one motor per muscle. One motor for the opposing muscle. So each muscle will still require a full motor. The advantage of my DC motor idea was counterclockwise releases the opposing muscle and pulls the main muscle. Clockwise releases the main muscle while activating the opposing muscle. So one motor handles two muscles. In a pneumatic system, one motor handles one muscle. So that's more motors. But the motors can be really tiny. They're just motors controlling valves on an air release valves. So space would be improved because they could be just the tiniest possible motors. Strength-wise, if you just have pneumatically filled bags creating the muscles, let's say in the arm, if you were to punch the arm, you'd be punching a bag. It would have no effect. So it'd be stronger. Price-wise, a pneumatic system would possibly be next to free. Because you could make your own muscles then. A pneumatic muscle could just be airtight, sewn together fabric. It could be made from nylon fabric. (1,000 denier nylon fabric, coated on the inside with a latex membrane, perhaps. Sewn together. So the fabric is just sewn into place. And then you just sew the ends of the fabric, or the ends of this muscle bag, into the tie-in points where a human muscle would tie in. Then you attach air hoses, which can be just shoved into the fabric in a hole. The air hose could be wrapped in cloth, glued on cloth, and then or taped on cloth, the double stick tape, and they can be sewn into the muscle. And then glue could be put around the sewn joint to make sure it's airtight. It wouldn't even need to be perfectly airtight. What's amazing about this system is there wouldn't be any risk of overheating. At least in, like, let's say the bicep. Because the bicep is just a bag full of air. You wouldn't have to buy... Well, okay, so you still have to buy tons and tons of motors, right? For controlling all the valves leading from the air compressor to the various muscles of the robot. But we're talking about $7 motors, the cheapest of the cheap, tiny, tiny hobby level motors. You know, super weak motors. And that motor connecting your homemade air compressor connecting its output tubes to a muscle bag, let's say the bicep. The tubing could just be hollowed out electrical wire insulation. Sewn into the muscle bag. Glued shut. Glue can fill any air leak. A cloth casing could be sewn around every single insulator tube. So that it doesn't rupture from the air pressure. Although I don't even think it would rupture. So a muscle bag would be sewn with its full contracted state in mind. So you would create the muscle in its contracted state, sewing it together out of nylon fabric. it would be oval shaped, and its ends would be tied into the bone, sewn in. And then as you extend the arm, for example, the bicep, that inflated bag which you created would get elongated, which the bag would be fine with. So you wouldn't even have to consider the elongated design. You just create the fully flexed design. And you'd model it after a fully flexed bicep. It'd look the same. It'd be the same volume. Maybe not the same. Because a fully extended bicep would be... Well, yeah, maybe it would be the same as the outer surface area of a fully flexed bicep. And then when it's fully extended, it'd be the same as the outer surface area of a fully elongated bicep. I could see that. Yeah, you just have to make sure it doesn't elongate too much. So you could create an internal rib framework to make sure the bag doesn't open too far. But even if it did open too far, that wouldn't matter. A fully relaxed muscle isn't doing anything anyways. I don't think it'd hyperextend. Plus you got ligaments to prevent against that. So it would just naturally be fine. My idea here is well, wait a minute. The advantage could be space savings and cost savings. And any concerns about overheating of motors savings. Because these muscle bags wouldn't overheat. There'd be no problem. They wouldn't wear out either. They'd pretty much last forever. Pretty much. I mean, all they're doing is inflating and deflating. They're just sewn together. If one of them ripped a hole, you could just sew a patch on. Talk about ease of maintenance. You wouldn't have to run power lines everywhere or cooling lines anywhere into the arm, for example. There would be no need for cooling at all inside the arm. You'd have your tubes running to every muscle. 2 tubes per muscle. And you just have all your muscles being just nylon fabric bags sewn together, homemade. You need 1 motor per muscle, which could be located in the torso. You'd need way less batteries for the robot, because the robot's going to be powered now off of combustion, off of gasoline or whatever your combustion fuel is, which is going to be what recharges the compressors, 1 or more compressors. It could just be 1 compressor in the chest. You still would need artificial lungs and a cooling system for all the little motors in the chest and for the onboard computers. All the little motors would just be valve motors. I don't know if they'd ever overheat. All they're doing is opening and closing little valves. I think overheating issues would be gone. The main compressor would probably need to be metal. It would fill through explosions. That would be loud, though. And it'd be regular. Loud and regular. You could implement a muffler system. You could create your own muffler to muffle the exhaust. Well, you wouldn't have an exhaust, would you? No, you would have an exhaust. Every time the muscles exhale, that would be your exhaust. Every explosion, the air would fill the air compressor. The air compressor itself could be designed to be a muffler as well. So the fuel would pour into the air compressor and explode, recharging the air compressor by increasing the total volume of air in the air compressor. That air would be very hot. You would need to cool that air down. Before it's usable, it'd have to be cooled down. I don't know if a combustion-charged air compressor is a good idea, because the air compressor needs to have good, clean, usable air that is an acceptable temperature for the tubing it supplies. Switching to all-metal tubing would ruin my entire robot. I can't have all-metal tubing and all-metal muscles, no. So the air compressor would have to have cool air, normal air. So the air compressor would need an air pump to recharge it. And the air compressor would need to be very strong to provide enough air for all the robot's muscular needs. An air pump would need to share an air intake with the artificial lungs. That gets sloppy then. The whole idea is starting to fall apart. See, even in a combustion engine of a car, the exhaust gases cause your muffler pipes or your exhaust pipes to get up to like 400 degrees. That's more than enough to melt plastic. So you couldn't have nylon muscles if you used compressed air generated by gases created through combustion. So the compressed air system can't be air generated by combustion. And that air would probably be difficult to cool, and it couldn't be cooled on demand quick enough to supply all the muscles with actuation power according to their needs. So now you're going back to a normal generator, a big heavy generator. That's a problem. Although, supposing a generator... I don't know if a generator could keep up with the needs of like a walking robot. Because he's just going to need so much air to keep filling all of his muscles as he's moving and doing all this complex stuff. So the amount of air needed would need to match the amount of air being used. Every time a muscle is flexed, that would represent a certain volume of air being used from the compressor. So the compressor would need to generate more than the total volume of air that all the compressors are using at once. Or that all the muscles are using at once, demanding from that compressor. I'm a bit relieved to come to that conclusion, because if it were possible, I'd need to redesign so much of my robot. And it's almost like starting over, if that were superior and possible. And the only reason I was willing to consider it all over again, even though I went away from hydraulics and pneumatics at the very beginning, was the fact that I had this idea of a compressor charged by combustion. But I don't think that that could work, because it'd just be too hot of an air supply, of an air source, for any of the actuators to be able to handle that kind of heat. And if it were able to be fueled by combustion, it'd be able to be recharged so fast, in demand, constantly, that a tiny air compressor could supply the entire body, because it'd just be being recharged so fast, like a jet, just like filling with like propane fuel, just like blowing hot gas, and they're just filling it with compressed air constantly, like an explosion. And so any air the muscles would need would get supplied immediately. But that's out. And a typical compressor wouldn't cut it. Hell, a pancake compressor from Harbor Freight can barely operate a HVLP spray gun to spray a car. It's not enough force, it's not enough PSI. So how is a pancake compressor going to power a robot? That's much more PSI and force required, I imagine. And a pancake compressor is bigger than my whole torso in volume. So that's out. And it's loud. Every time it needs to pump up air. No. I ain't gonna have that loud stuff. Yeah, a air compressor would just be way too slow at giving the robot enough air. It'd have to be way too small to fit in the robot's body. It just wouldn't work. Maybe if you were able to cheat and connect your humanoid robot up to a full-size, you know, mechanic's garage-size air compressor with a hose, and then the robot runs off of that supply. But I want a mobile robot that can go outside. It's not stuck being tethered to a gigantic commercial air compressor. That's unacceptable. So that's the only way a pneumatic robot could work, is if you have a big old air compressor he can be tethered to. But that's too restrictive and not nearly as impressive. You bring the robot to a robotics competition, I don't even think that would fit the rules of like the DARPA robotics competition. You need your robot to be able to hop in a car and drive it around. You can't have your robot lugging around a gigantic AC powered commercial air compressor.